Okay, so we have again Dr. Oliver Schulte from the SFU School of Computing Science. He's going to be speaking about machine learning in sports analytics. Dr. Schulte is a professor in the School of Computing Science. He received his PhD from Carnegie Mellon University in 1997. He's published papers in leading artificial intelligence and machine learning venues on a variety of topics, including sports analytics, or learning sports analytics, causal graphs, and game theory. Growing up as a soccer fan and a competitive chess player, so I just want to emphasize that he was an exceptional chess player. I don't know, he can clarify, but I believe he played Kasparov or at one point in his career. But in any case, he's been intrigued by strategy and tactics and physical and other games. And I just want to add that Dr. Schulte is also, he has degrees in philosophy as well. He's a true Renaissance man and a very, very interesting and intelligent fellow. So I highly recommend that you check out his website and learn more about his work. So with that, I will turn it over to Dr. Schulte. So Oliver, I'm going to just pause my, or turn off my screen share and have you take over. So I just got a message that he has the rank of international master, and there's only one rank higher than that. Very impressive. So Oliver, are you there? Can you share your screen, please?
I believe I unmuted myself. Did that work?
Okay. Welcome.
Okay. And let's go here. Thanks for the introduction. Yeah, this game with Kasparov, I think it was when I was 17. And sometimes I think I peaked early, you know. Everyone.
That's a common problem in sports, isn't it?
That's true, yes.
Okay, I'm going to mute myself and I'll let you carry on.
Okay. So yeah, thanks for attending my talk, and thanks very much to Dave for organizing. I know he's super busy with many things, including the remote teaching and COVID situation, so I'm just putting a lot of time into this. Yeah, I wanted to talk about some ideas in machine learning that at least give you, I think, a new approaches to problems in sports analytics. Aiming for a fairly brief talk, 30 minutes, and definitely high level, and then we can go a deep dive depending on what you're interested in. Did that work? Everyone sees a new slide? Yes?
Yeah, I'm good on my end.
Okay. Let me start by asking, why is sports analytics difficult? Probably a question that this group could discuss for a while. And I do think it is difficult. Sports data are harder than many data that you would see in introductory statistics or machine learning. And I think that's for three main reasons. So one is you have complex interactions, interactions among the variables or features that you're observing, players, events. Everything is combined in a complex nonlinear way. You have dependencies, so different observations at different times are not independent of each other. What happens on one place on the rink or pitch influences what happens at other places. And you have heterogeneity, lots of differences, players, teams. And I think one of the really interesting challenges in sports analytics is to cover what players have in common and how they're different. So you really want to capture both. I thought about going into this, but to keep this sort of brief and self-contained, I think there's one issue that I may have to come back. But so I won't go into that further today. If you look another way, usually introductory statistics, we start with IID data, identical or independent, and game events are neither of those, player are neither of those. So it breaks the assumptions. It's not just statistics. I've taught introductory machine learning, and I think it's only like 2 weeks out of the course that we devote to data that are not IID. What I wanted to do is present some ideas from machine learning to address these challenges. And one in particular is the problem of tracking chances of success as the game unfolds. That's a problem that's been worked on a lot in the last 20 years in a field called reinforcement learning. And they have very powerful ideas that I think can be used in sports analytics, but that you wouldn't have heard about, I think, just from, unless you really made an effort to study reinforcement learning. Okay, so I'm going to talk a lot about what I think is new in machine learning. So let me start by saying that there's a lot of truth in this cartoon or meme that's been going around the internet, right? You start with statistics, you dress it up, then you say it's machine learning, and then if you have to sell it, you say it's AI. So to the extent that AI has been successful recently, it's because they've used a lot of machine learning. And to the extent that machine learning works, it's because it's built on statistics, where you have a rich body of analytical tools, concepts, models, algorithms, everything you want. So, so maybe machine learning is like the youngest child of statistics. So let me get to start with variable interactions, and wanted to discuss a problem that where this comes up, the question of complex interactions, and Peter Tingling and I have done separate work on this, on the draft problem. And the draft problem is basically you have player stats from junior leagues, and you want to ask, are they going to make it to the professional league, and how are they going to do in the professional league? Now, what does it mean? How are they going to do in the professional league? So Peter Tingling had the proxy of asking how many games played after 7 years, and there's been follow-up work using that by Schulte, for example. We also did that, and another question I looked at another way to phrase the question is, are they going to get into the NHL at all? So we spent time scraping data from the web and collecting it all. And at one point I asked Michael Schulte whether, I said, oh, you've done all this scraping. Can we have your data set? And he said, no, it's too messy. I don't want to share it. So to avoid a third pass through eliteprospects.com and such, we posted our data, so you can go download this. And just to give an idea, so let's say you're interested, as I said, in the number of games played in the NHL after 7 years. And you say, well, I wonder if the CSS rank predicts that. And the CSS rank is the Central Scouting Service. So this is shared information about the NHL team, where the scouts go and look at the junior leagues and rank the players. So now if you do what's called a partial dependency plot, so you say, okay, this is my target. I'm just looking at one variable for now. You can see it's very messy. It's non-linear. You do get some relationships. So you can see there's a lot of zeros along here, right? So most prospects don't play in the NHL at all. On the other hand, if you're in this realm here where the CSS rank is high, so number 1 is the best you could be, you can see that there's a nice column of players playing quite a lot. So there's relationships here, but they're certainly complex. And if you want to explore this more, we actually made an interactive plotter where you can pick anything you want. You can pick CSS rank, you can pick their goals, their plus minus, and then you can make similar plots. You can filter by league, you can filter by season. So I think it's a nice exploration tool. So I want to plug it because my student especially put a lot of work into it. Okay, so the data looks something like this, right? We want to predict the number of games played. We have things like the CSS rank, player stats from the junior league. So here I'm just making up some generic stat. And then we also have things like their age, the weight, the height. And then we have a specific player, and we want to predict whether they're going to get to the NHL or whether or what the number of games is. pausing. Okay. Okay, so now I'm going to introduce a tree model as a formalism for capturing complex interactions. If you've seen a decision tree, we're using a model tree, which is like a decision tree, but instead of having a unique decision in the leaves, it has a logistic regression model. Okay, so I'm going to explain this, sort of walk through this now. So this is, again, produced by a program. Okay, so you just give it the data, roughly like what I showed you just in the previous slide, and it comes up with this. So it's fine. This is completely data-driven. And so at the root, it puts what it thinks is the most important variable for predicting whether a player gets to the NHL or not. And that's the CSS rank. So that's reassuring because presumably the scouts know what they're doing and they're paid a lot of money. So presumably their rank carries a lot of information about how future performance of players. And then what these tree models do is they split. So they learn thresholds. In this case, it's 12. And you can think of that as like a critical value. And so this tree says, okay, if your CSS rank is above the critical value, so that's good, right? 1 is the highest. Then you can be quite sure that you're going to make it, that you're going to appear in the NHL. So here we have, if you look at the group of players that satisfy this criterion, then almost 82% of them actually make an appearance. Okay, so I'm just pausing. So that's the idea. Okay, so that's how to read these trees. So now the interesting case from a predictive point of view is what if you're not in this elite group, right, of the clear stars? So what if your rank is below 12? Then the tree says, okay, the next thing we should look at is the points. Points regular season in the junior league. And then again, there's a critical value, happens to be the same number 12. So if you're below 12, then the prospects are poor. Okay. So you're going to be, this group of players, only 16% of them ever make an NHL appearance. And, but also I want to say, we have actually a model inside of this leaf. So it's not, 100%, we use the features then to make a further prediction. But now let's suppose you're ranked low by the CSS people, and then but your points are high. Okay? So now I won't go through the whole tree, but here's, for example, an interesting group. So suppose your points are high, then the tree wants to look at your plus minus from the regular season. And then suppose your plus minus is also high, and then your assists are also high. For the playoffs. So now you're in a small group, but an elite group that actually, these are real diamonds in the rough. Okay? They're ranked low by the CSS, but their other stats are good, and they actually have a very high chance of making it to the NHL. And if I remember correctly, Canadians are somewhat overrepresented in this group, and Brant Marchand was in it when he was drafted in his draft year. So one point is that you can see how this tree is capturing nonlinear interactions, right? It's looking at combinations of variables, nonlinear combinations of these variables, and you saying that, oh, it's the combination of these particular features that places you in one group. I also think it's a nice way to think about drafting because it gives you groups of comparables. So this speaks to the question of how I said, we have heterogeneity, right? So you can say, oh, I can actually now put players in a group, and I can use the regression model to say what makes you exceptional in a group. So we have all this in the paper. But if you look at a lot of the draft approaches, for example, Sony's drafting tool, they always give you comparables. They say, oh, we think this is a strong player, and when Sidney Crosby was his age, he had similar stats. So I think the tree is combining a regression approach and a groups of comparables approach. And we also did this for NBA drafts and so forth. But anyway, so as far as I can tell, it gives you everything you want. You can understand it, you can explain the predictions, it gives you predictive power, and it gives you this grouping into cohorts. Okay, no comments on the tree. It's like teaching on Zoom, there's no feedback. Okay, so there is another way to model complex interactions using what's called a graphical model. This one's hard to read, so I'm going to try to switch to my actual software here. I can find it. Here it is. Okay, I think this is easier to read, I believe. You guys seeing, it should say something like belief and decision network tool.
Yep, looks good, Oliver.
Yeah. So this is called a Bayesian network or causal graph. We discussed those in the last session 2 weeks ago, actually. So this was learned from box score data in the Premier League. So, and you can actually learn these graphs. I think that was a question that came up 2 weeks ago, right? So one thing is you start with a causal graph and you say, okay, what can I infer from this causal model? But you can actually do a data-driven approach. And then when you do that, you can think of the graph actually as learning the complexity of interactions. So let's say, for example, if we look at dribble efficiency, it has 2 parents. So let me move this so it's a little easier to see maybe. And where's the other one? Position ID. Okay, so it has 2 parents, position ID of the player and time played. So the way you can read that is you can say that these 3 are variables, time played, dribble efficiency, and position ID, engage in a 3-way interaction. Okay. And then let me see, so shots on target would be involved. It has 3 other parents, so it would be involved in a 4-way interaction, right? So instead of assuming that maybe all the interactions are pairwise or that they're of a certain form, the graph actually tells you how complex the relevant interactions are. And then once you've built this, you can actually explore the data quite nicely through some queries. Let's see. I guess that's okay. So you can run probabilistic queries. I'm just going to give a couple of examples. So what this is saying is, if I look at the dribble efficiency of a random player in a random match, 48% of the time it's low. So we discretized all these continuous values, which kind of hurts me to do violence to the data like that, but it's sometimes easier to use discrete data tools. 18% of the time, 18% of the matches, a random player will have a medium dribble efficiency, and 34% of the matches will be high dribble efficiency. Right, so it's compressing the data. And then you can do things like, oh, I wonder what influence, let's say, the amount of time that a player plays in a match. I wonder what influence that has on dribble efficiency. So if they play a lot of time, not very much, okay, if they play small amount of time, 0, oh, then their dribble efficiency is likely to go down. So you get to 0. So that's kind of interesting. Do we believe that? Maybe not, but you can use these queries to explore all kinds of correlations in the data and what is the effect of changing team formation. What about different position IDs? Do different position IDs have different dribble efficiencies? Okay, so you're capturing the complexity of the interactions in a data-driven way, and you can then explore at least various correlations in a kind of very intuitive, graphical way.
So Oliver, there's a couple of questions and comments.
Yep.
I'll pass these along. So first is from Dr. Ian Schreier at McGill. He states that this is only one type of causal graph. It is not a directed acyclic graph because there are cycles between variables. Causal graphs do not deal with interactions unless you are defining interactions differently than statistics. There must be additional information being encoded that are not necessarily part of a causal graph. Can you provide a reference for how you're using these terms, please?
Well, there shouldn't be cycles in here. I mean, it's kind of too big to eyeball it, but so this program is like a kind of interface program from UBC. I think it wouldn't actually load the graph if it had cycles in it. So that's yeah. So it should be anyway. But maybe there's a bug here. But I definitely mean a directed acyclic graph. Whether you can always interpret a DAG causally, that's another question. And yeah, interaction. I guess I just mean that. When you're, say, predicting, I give the example of dribble efficiency. Yeah, well, it's maybe not so easy to define. Yeah, I'm struggling a little bit to say. So graphically, it's like an exponential model with a clique where the potentials are associated with cliques, and then the size of the clique is learned by the model. And that's what I mean by an interaction. So if the clique has contains 3 nodes, then it's a 3-way interaction. But if you have in mind a specific term for interaction, I'm not so hung up on that. But the important thing is that when we're looking that we're looking jointly at that we have a small model that jointly models the relationship among these 3.
Okay, so Dr. Schreier, if you want to chime in, please do so. I'll just follow up with your second part. And so he asks, if this is data-driven, maybe mean a graph created out of causal discovery as opposed to causal inference?
Yeah. So it runs a causal discovery algorithm.
Okay, and so there's another question. Is the model learned from data? So I believe you say it was data-driven.
Yep.
So the answer is yes. And can you just remind people what the data set was?
Yeah, it's from the Premier League. It's called box score data. So for every match and every player, you have, for example, the number of goals that the player scored in the match. You have the time that they played in the match, whether or not they scored the first goal. So you have, I have the data set also posted on my website actually, but yeah.
Okay, great. So if anyone wants to follow up, please chime in now with your voice. Otherwise, I'll ask Oliver to keep going.
Yeah, I'd be interested in a discussion of the interaction. But okay.
Great, thanks.
Yeah. So let's go back to the PowerPoint. Am I back in the PowerPoint?
Yeah, you've got your presenter view on right now on the screen.
Oh, really? Does it say model non-specification?
Yeah, so we have your PowerPoint. It's just that you're sharing your actual presenter view versus just the slide.
How's that?
Still in presenter mode, but maybe...
Oh, okay. Wait a minute. I think I know what happened there. Sorry, I got...
There you go.
Okay. I forgot. Oh, that's interesting. I got two desktops two displays in my office, so... And they're both showing it, but one is doing presenter mode and one is doing this. Okay, so so that's, I think, two examples of handling of how you have two data-driven models. And I think some of the issue is around specifying models or possibly misspecifying them. So I wanted to kind of zoom out a little bit from even sports right now and reflect a little bit on statistics and machine learning. So ideally, we want a parametric model where we have the right functional form and we wanted to make accurate predictions. And often that we get that, for example, in physics. For another example, shows this from sports, from, for example, Ugarte et al. Report that if you look at the average number, if you look at the number of goals in a World Cup, Soccer World Cup, that the Poisson distribution is adequate. I haven't checked that, but let's assume that they're right. I'll give the reference here at the bottom. So then you have a great situation, right? So you know the right form to use and you can make accurate predictions. Now, often what happens, I think it often happens in sports analytics, is you can't get that. So you have to make some choice. And you can go, and this happens often in modeling, that you have to choose between an exact solution to the approximate problem or an approximate solution to the exact problem. So you could say, I'm going to go ahead with a linear model, and that's interpretable. But if my phenomenon is actually not linear, then I won't get very accurate predictions. Or you can say, well, I'm going to emphasize accuracy and go with a model that makes few assumptions and therefore is likely to fit the data because it makes few assumptions. And maybe then I won't be able to interpret it, right? I'll just get good predictions. And I don't know that one way or the other is better. I think, for example, what we saw in the linear model last time, often you want to answer causal questions, like does crossing actually have an effect? And does it maybe have more of an effect than other actions? And it's not so important to really predict whether the team is going to get a scoring chance or not. So what I think has happened in machine learning is that there's been a strong emphasis on accuracy, and that drives them towards what in statistics would be called a non-parametric approach or a function approximation approach. So I don't even endorse that particularly, but I'm just observing, but I think that's where the field has ended up. There's a classic discussion of this kind of distinction by Bryman, going a way back, but I think it's still worth reading. More recent one from an AI point of view by Sutton, so I'm giving some references. And And sort of the kind of extreme version of that really is to go with something like a neural net, which is a universal function approximator. Right? So you can actually prove, right, that yeah, at least in principle, you can approximate any function that you might want to with any desired degree of accuracy. And I'm going to try to see, I have a little demo, if I can make that sort of visual. Okay. Are you now seeing, should be saying something like tinker with the neural network right here in your browser?
Yep.
Yeah, okay. So at a neural network, so it's a nice demo. So here what they've done, so here what you're seeing on the right is a set of data points in 2D, and they're labeled with the right class according to, so orange would be, say, the positive class, blue would be the negative class, right? And then underneath, you're seeing the current output of the neural network, which is sort of, it's hard to see actually. All these points are kind of weakly orange, and all these points are weakly blue. So this is before training. And so now if you say, okay, this is the function, right? So think of this as a function that maps points in 2Ds to 0, 1 labels that I'm trying to approximate. Then when you run the neural network, it goes on and it creates some approximation. And you can see it's not perfect. You know, I didn't let it run forever for very long either. So it has some here, but it's getting this kind of decision surface approximately right. You could try another one. Let's say this function, and right where you have the blue inside the orange, and you can use the same setup, and you can now say, okay, now please train this so that the neural network gives me approximate this surface. Right? And you can have a demo where you can show, oh, suppose I have a linear function. Oh, you can train a neural network to approximate a linear function. Oh, suppose I have a sine function. You can train it to approximate a sine function. And so at a high level, that's kind of all you need to know actually about a neural network, that in principle, you can get some approximation to your function if you have enough data and you have enough computation time. I just wanted to show briefly what these things look like, if I can find it. Maybe I cannot find it. Sorry. Well, I guess maybe it doesn't matter. Okay. But it's really, you're on the left. I mean, you're kind of seeing how the neural network works here. So the 2 input features are connected to 4 intermediate features. And so you can see how, in principle, everything is connected to everything else. So maybe I shouldn't use the term interaction, but that's what I mean by complex combinations can be learned. But, you know, it's hard to say what each of these intermediate features is doing. There's no closed form that you can point to. So you just say, oh, I'm getting something that's approximating my data. Let me see, I gotta get to, go back to my presentation. Here's an example that we've done on sports, and I'll discuss the details later.
Hey, Oliver, we're back in presentation mode.
Oh, okay. Hang on. How's that?
Beautiful.
Yep. Now I've learned what's causing this. So suppose you wanted to plot something like as a function of rink location, say where the attacking team currently has the puck, what's the chance that they're going to score the next goal? Okay? I'm going to discuss this more in a bit. But so roughly think of it as scoring chances on the rink. And so you can imagine that, right, for every location there is such a number. And but what is the right functional form for that? Who knows? So we trained a neural network, and I'm going to explain in some detail how. But we trained a neural network to do this, and here you see a heat map of the output. And so red means higher scoring chance, and it kind of makes sense, right? So you're sort of around this ellipsoid from the goal, and it fades as you move further away, right? But it would be hard to certainly say a priori what the right parametric form is. Okay, so right, so those were some of the themes about complex, well, let me call them interactions, and you know, using a non-parametric model, using a universal function approximator, so you're not specifying the model. And now I want to talk about a specific problem in sports analytics, tracking evolution of success probabilities. So the problem is this: given the current match state, what is the chance that the home team will succeed in the future? Right? Now, success can be various things. It could be winning the match. It could be, oh, scoring the next goal. It could be, oh, we want to make it so that the other guys have a penalty. It could be, oh, we want to be able to cross. Okay. So this theory is very general in that respect. And so again, you can say, oh, okay, so what I have here is a function, right? I take as input the current match state, and I want as output a number that tells me what's the expected future success. So a function like that is called a value function in machine learning, specifically reinforcement learning, because really it's the expected value of the team's current strategy given the current match state. So I want to give some examples. Maybe the most familiar example is win probabilities. So so this is a graph, Toronto versus Golden State, a great moment in Canadian history. And you can see how at every point in the game, it's from ESPN, they actually, they give you a win probability, and you can see it changing over time. And in the end, it goes to 100% for Toronto because they're at the end of the game. Right? And yeah, anyway, you can go, I gave the link, you can go check it out, you can play with it, they annotate with events. Here's something that we did for an NHL game. So you can think of these as value tickers. It's a little richer, so we're saying, okay, what's the chance? Blue is the chance that the home team is going to score the next goal. Orange is the chance that the Penguins will score the next goal, and Q is, there's also a possibility that neither team scores the next goal. Okay, and then you can see, for example, in the beginning where we're starting our ticker, right? The Penguins are launching a dangerous attack, but they're actually not scoring. And here's another dangerous attack, and then they actually score. And then the Blue Jackets go back on the offensive. Okay, so in this way, the success chances are evolving. Luke Boren built a system with where you track the expected possession value. So this is the probability in soccer that a given attack will lead to a goal. And again, actually he has a nice video, but I think I won't take the time to show this now. So he has a method, right? He has a ticker and he annotates this with events. Maybe I'll have time later, I'll show the video. Okay, so I hope this brings across this idea, okay, that's what we're trying to do here, is we're trying to match every time point to a expected success. So motivation for this problem, well, it's important in itself. Okay? So often, for example, you want to predict the match outcome. You can also use this to evaluate players and actions. And the idea is that you define the impact of an action to be the effect that the action has on the success probability. So if I go back to this one, for example, the action here raised the success probability by a lot. Okay, so that was a good action, even though it didn't lead to a goal. It took your team from a less promising to a more promising situation. And so this idea has by now, so in the last 5 years, many people have developed this as an idea for player ranking. So myself in ice hockey, Luke Bourne in basketball, and now in soccer. We're also working on soccer. Marty Puderman in the National Football League, and so that and it always seems to work quite well as a player evaluation tool. In fact, Cervoni, so the Harvard Sports Analytics group, they wrote that most questions that coaches, players, and fans have about basketball, particularly those that involve the offense, can be phrased and answered in terms of expected future success. So I actually think it's the most important problem in sports analytics is to get these value functions. So I wanted to take the last bit to talk about methods for learning these, and this is going to be high level, and in particular this idea of temporal difference learning. So reinforcement learning deals with this problem very generally in any sequential decision problem, and there have been many successes of the field, over the last 20 years, and there's well-known breakthroughs. So, for example, DeepMind has built world-beating chess program, Go program, now StarCraft. So all those programs that you may have read about, they're using reinforcement learning, and in particular using this temporal difference technique that I want to explain. And the basic problem here is that successive observations are dependent. So in terms of statistics, we're in the realm of stochastic processes. And I think one of the things in machine learning is that machine learning gives you tools that make it maybe a bit easier to analyze the stochastic processes, even if you haven't taken the course in the subject, which you should if you can. Okay. And so I want to, for this specific problem of estimating success probabilities, I want to explain some of these tools. So typically we have continuous data in sports, particularly with respect to sports space and time. And you can do a couple of things. One is you can discretize the data, okay? And I've done that, for example, for hockey. So for example, you can divide, say, the rink into grid cells. And then you can apply a technique called dynamic programming or value iteration, which is very important, a very efficient technique for estimating success probabilities when you have discrete states. So when, for example, when you're at a discrete time instant and discrete locations. You can also, instead of discretizing the data, try to work with raw data immediately, directly, so continuous time and space. So then you have a further choice whether to choose a parametric transition model or not. So this is reminiscent again of, do we specify a model or do we try to work in a non-parametric way without specifying a model? So this paper by Cervoni, Bourne et al. In basketball is very sophisticated development of parametric transition probabilities. So it's definitely possible, and I recommend it. What reinforcement learning has worked on is the idea of using not specifying a model. So they call this model free, which I kind of wish they wouldn't, but anyway. So it's more like a non-parametric approach. And then how can you learn with that? Well, that's this temporal difference learning idea. That's where the last piece today is I want to explain, give you an idea of how temporal difference learning works. Because it's very powerful idea. As I said, it's used successfully in pretty much all modern reinforcement learning systems. And it's very little known, I think, outside of reinforcement learning. So that's a message I'd like to spread. And at a high level, here's the intuition about it. So you start at some random place and with some random estimated value function, and then you keep improving it. And then how do you keep improving it? Well, the intuition is that you want your estimates to be consistent. So it's something like this, right? So right now I'm estimating my chance of success. Then I observe what happens. I say, oh, maybe I was right or wrong. I'm going to change my estimate of success. And it's that difference that you're trying to minimize. Okay, I'll give an example in a minute. That's probably easier to follow. Okay. But at a key level, it's exploiting the idea that successive observations are correlated. And therefore, to the extent that I'm changing my mind about success probabilities, I actually should be improving my model. So one beautiful thing about it is it's exploiting the dependence. Instead of having it be something that breaks your assumptions and your learning, it's something that you're using in your favor. Okay, so let me work through an example, and I think this will make it pretty clear. So suppose we have a match state, and this could be something quite complex. But let's just say it's something like score differential, and is the team on a power play, and right now they're in the defensive zone. And I'm estimating, okay, 55% chance that they're going to score the goal. Okay, and then let's look ahead one step, and now they actually don't score a goal, but they get closer, they make it to the offensive zone, and I'm going to change my estimate to be 70%, right? So you can think of it this way. At first I thought, these guys, who knows how they're going to do, only 55% chance. And then I see what happens. I'm like, wow, they're actually doing really well. I underestimated them. So mathematically now you're saying, well, really my 55% should have been 70%, right? So I'm taking this as a squared error signal. Now here they are doing very well in the offensive zone, but then actually, even though they're on the power play, they're not using it. They're losing the power play without scoring. So now their chances go down to 58%. So now at this time step, I say, oh, actually, I overestimated them. Okay. So now the difference between my successor estimates become my squared error signal. And then let's say they actually managed to score, even though they're at even strengths. Okay, so now I say, oh, wait a minute, I said they have only a 58% chance, but they actually scored. So now again, I get a big error signal. Right? And so now what I can do is at every point, right, I now have a concept of an error, and I can change my neural network so that when I give it this input, it minimizes this error. When I give it this input, it minimizes this error. When I give it this input, it minimizes this error. Okay. And that's basically it. Okay. Well, there's more details and things you can set differently, but that's the key idea. Okay, and then let me just contrast that with, here's something that many people do, and I've seen many people do in sports analytics sort of instinctively, is that they turn it as a regression problem. So they say, okay, these guys, where they had a possession, what actually happened? Oh, they scored. What I'm trying to do is I'm trying to say at the beginning of the possession, what was the actual outcome? So that's what I'm trying to predict. So, right, so now I treated, now I would say, well, I said 55%, but actually it was 100%, or you could treat this as a logistic error, but that's not so important now. So the difference here is I'm taking as my target the actual outcome, right? And I say, oh, at every time point I was trying to predict the actual outcome. So now let me train my model so that it basically becomes a regression problem, right? This is my input, this is my output, this is my input, this is my output, this is my input, this is my output. Okay, and that is very natural. As I said, I see many people sort of adopt this idea naturally, but it doesn't work as well. Okay, so I've done experiments, lots of people have done experiments in other settings. I've done them in ice hockey. And the problem with that is now you're using an IID technique, namely regression, right? You're treating each of these rows as if they were independent data points that you're fitting. Okay. But really, right, the success probabilities are highly correlated. Okay, so that's my rant, I guess. Okay, so let me conclude. Okay, so sports events not independent, right? There are all kinds of complex interactions among players, events, variables. If you're looking at nonlinear interactions among variables, you can represent them using tree models, graphical models, and also neural networks. And then the main problem I want to talk about today is predicting a team's future success. And just the message I want to get across is that that is a key problem extensively addressed in a field known as reinforcement learning. And, you know, the sort of leading method there is the temporal difference methods, which I think for sports has the great advantage that you can work directly with continuous space and times. And it doesn't make parametric assumptions. Again, if you have parametric assumptions that fit your domain, great, you should use them. But if you don't, then this is a good baseline method. I made a whole set of references here. So like if you want to see more about reinforcement learning in general, and then in particular applications to sports, most of which I mentioned as I went through. Okay, thank you for listening so far. Happy to chat more, take questions.